And now I want to take another look at rate of change, and I want to apply it a little bit. Now, in your textbook, they have applications to social sciences, economics, biology, lots of good applications, chemistry even. But I want to stick to something more directly in line with where a lot of you are going to be going. So I'm going to look at more of a physics type of application here. But first, a reminder. Remember that if you have something that is undergoing some sort of change, for example, if you're graphing, I don't know, motion perhaps, and you had a couple of x values, an x1 and an x2, a couple of ordered pairs associated with them, and with those, you're going to have a y1 and a y2. Remember, and this is as much as just remembering the terminology as anything, remember delta x means change in x, which would be x2 minus x1. Remember, delta y means change in y, which would be y2 minus y1. Now, of course, if this curve is being defined by a function f of x, then delta y, change in y, is also f of x2 minus f of x1. Therefore, our difference quotient, which is delta y over delta x, which, if you recall, is how you defined slope many years ago, but that would be f of x sub 2 minus f of x sub 1 over x2 minus x1. That is your difference quotient, and that is the slope if we were to connect a straight line to these 2 points. But since this curve isn't a straight line, this isn't the slope of the curve between 2 points. It is an average slope. In other words, this isn't the rate of change of the function. It is an average rate of change between these 2 points over the interval from x sub 1 to x sub 2. And again, in many fields like economics, biology, chemistry, physics, you deal with things that are changing. And even though average rate of change is a good thing to know, instantaneous rate of change is often very important. To find instantaneous rate of change, perhaps maybe at that point right there, what you would want to do is use this point and points close to it, maybe this x sub 2, maybe this x sub 1, maybe a little bit of both, and bring these points closer and closer together to turn this average rate of change into an instantaneous. In other words, what we want to do is find the limit of this difference quotient as the delta x approaches 0. And we've defined that symbolically as being our dy dx, which we all know as the derivative. Now, previously, this was a little bit difficult to work with, but now we have some techniques for taking derivatives, some shortcuts, some formulas, and answering questions like this, therefore, has become a lot easier. So let me grab an example from the exercises, and let's walk through it. Let's say that a particle's position at time t is equal to t cubed minus a 12 t squared plus a 36t. Now, this is the way they'll write it in the book, but I've always preferred to use the proper function notation. And here are the types of questions you're going to be asked. You'll be asked, number 1, find velocity at any time t. Well, remember that if s is a position function, then the rate of change of position is velocity. In other words, velocity at time t is s prime of t, which is something we no longer have to find using a definition. I can simply use my rules. First of all, power rule. This can be a 3t squared, because the 3 came down, the power reduced, times the derivative of t, which would be a 1. I'm not going to bother writing it this time because it's an application. Minus, again, the 2 comes down and gets multiplied, it'd be a 24t times a 1 plus a 36. So the first derivative of position is velocity. And what this will allow me to do is find the velocity at any time. If they were, for example, to say, what's the velocity at time 3 seconds, then v of 3 would be 3 times a 3 squared minus a 24 times a 3 plus a 36. And that's going to be a 3 times the 3 squared minus a 24 times a 3 plus a 36, and it is a -9. Now, it may seem a little bit strange to you to get a negative answer for velocity. There are a lot of people who think velocity always has to be a positive number. How do you travel at -3? What units would we be, feet per second, or -9, or something like that? Well, velocity is a vector. That's the thing to remember, is that velocity is a vector. So a negative number just implies a direction. So in this scenario, there's going to be a forward direction and a backwards direction. And it would appear that at 3 seconds, we're heading back to where we came from. All right? If they were to ask, when is the particle at rest? Well, you are at rest when your velocity is equal to 0. So I would take the 3t squared minus the 24t plus the 36, and I would set it equal to 0. And I'm hoping they're giving me some nice numbers for this, so let's find out if we can do this by hand and not have to use something like a quadratic formula. I'm going to factor out a 3 first. And then, maybe it'll be nice to me and let me factor this. So it would appear the particle's at rest at time 6 seconds and at time 2 seconds. So what might be helpful is to start getting a basic sketch of this particle. All right, we'll say down here is time 0. And here's time 1, 2, 3, 4, 5, 6, 7, 8, and I hope that's enough. I hope I don't run short. All right, so at time 2, it is at rest, and at time 6 is also at rest. All right, so let's see what else they want to know. When is the particle moving in the positive direction? And I would add to that, when would it be moving in the negative direction? Well, if it's at rest here and here, then it must be in motion in these 3 intervals that this cuts up. So let's just plug in a 1, for example, and see what's happening. Velocity at times 1 is going to be a 3 times a 1 squared minus a 24 times a 1 plus a 36, which is a 3 times a 1 squared, which is going to be a 3, of course, minus a 24 times a 1, and that part's going to be a 24, plus a 36, and that's 15. The 15 isn't the big deal. 15 just means it's moving in a positive direction, which means forwards. All right? Coming over here, at this time frame, I've already checked out the 3. I've already got a negative result from that. So this means it's moving in a negative direction. So what this thing did was it left its starting point, it moved forward for 2 seconds, moved into the positive direction for 2 seconds, moved into the negative direction after it started moving again, stopped 6 seconds out from the beginning. And let's see what's doing at 7. Velocity at times 7 is 3 times a 7 squared minus a 24 times a 7 plus a 36. All right, let's check that out. 3 times 7 squared minus a 24 times a 7 plus a 36. And that's positive again. All right, so it started at time 0 from wherever it was, moved in a positive direction. At time 2 seconds, came to a stop, moved in the other direction up until time 6 seconds, came to a stop, and then turned around and headed in the positive direction. So since I went from positive to negative here, that means it turned around here. Negative to positive there means it turned around again. And this is what the velocity did. This is all about velocity. All right? It wants to know what the total distance was that it traveled during the first 8 seconds. Okay? Total distance traveled during the first 8 seconds. All right? Well, how would we figure that out? How would we figure out how far it traveled in the first 8 seconds? All right? Any thoughts on that? Well, one thing you're going to have to take into consideration is the fact that it's moving back and forth. All right? It's moving back and forth. So what we're going to have to do is look at these intervals of time, right? Look at these intervals of time individually. And we're going to have to use our position function. We need to go back to position. All right. So at time 0, let's look at these times. At s of 0, that one's really easy to plug in. You get 0. So at time 0, it was at location 0. And then it started moving forward, positive direction. So at time 2 seconds, let's see where it was. So if I go 2 to the 3rd minus 12 times a 2 squared plus a 36 times a 2, it's at position 32. All right, so it moved a distance 32 units in the first 2 seconds. And then what did it do? Well, next we need to look at this 6 second time block. Where was it at time 6? Well, at time 6, it's going to be 6 to the 3rd power minus 12 times 6 squared plus a 36 times a 6. And at time 6, it's back in location 0. So it moved from position 0 to position 32 in the first 2 seconds. By the time we got to 6 seconds, it was back to position 0, which means distance traveled is another 32 units. And that's what it's asking for. It specifically said, if I remember correctly, let me look at the question again. Oh, no, first 8 seconds. I want to know, where did it travel in the first 8 seconds? So we need to figure out position at time 8. All right, almost forgot about the last step. 8 to the power 3 minus 12 times 8 squared plus a 36 times an 8. And it's back at position 32 again. All right, so it went 32 units out here, came back 32 units, and then went back out 32 units. Add them together. Total distance traveled is 96. Okay, total distance traveled is 96. So you have to take these different, basically you would call it legs of its journey, and figure them out one at a time. And what I was doing was not taking any regard for direction. In other words, I was basically, in my head at least, looking at absolute values, because again, distance traveled isn't something you should figure direction into. Distance is distance, no matter what direction you travel. All right. So there is its distance traveled in the first 8 seconds. And the last thing they want to know is, when is it speeding up and when is it slowing down? And to understand that, to answer that question, we have to understand what it means for something to speed up and slowing down. All right. Here, you notice it started from position 0 and went to position 32. And by the time it hit position 32 at 2 seconds, it had stopped. So in here, at some points in time, it was speeding up, and at some points in time, it was slowing down. Same thing here. It started going backwards in a negative direction, but it came to a stop. So at some places in here, it was speeding up, and some places in here, it was slowing down. So what does it mean to speed up, and what does it mean to slow down? Well, if you're moving forward and being pushed forward, you're speeding up. If you're moving forward and being pushed backwards, you're being slowed down. If you're going backwards and being pushed backwards, you're speeding up. If you're going backwards and being pushed forward, you're slowing down. In other words, when velocity and acceleration are heading in the same direction, you're speeding up. Whether that's both of them forward or both of them backwards, you are speeding up as long as they are pushing in the same direction. So, long story short, we need to add to this an acceleration function. So, my velocity function was right here. And acceleration, therefore, is going to be the derivative of velocity, which is the second derivative of position. Acceleration is going to be, again using my shortcuts, a 6t minus a 24. Much more simplified function. And therefore, I need to set up an acceleration number line, much like I set up a velocity number line. So I'll take the 6t minus 24 and set it equal to 0, just to know where my zeros are. 6t equals 24. T there, 4 is a 4. Okay, so we'll say that 0 is down here somewhere. Here's 4, and here's everything else. Plugging a number in just to see what's happening. Say like maybe a 1. Well, acceleration at time 1 second. So 6 times a 1 minus a 24, which is a negative 18. So in this interval, acceleration is negative. Putting in a number like maybe 5, acceleration at time 5 is a 6 times a 5 minus a 24, which is 30 minus 24, which is a 6. Not caring about the 6. I care about the fact that it's positive. All right, so if we lay next to that our velocity number line, sort of recopy it from what we had here, what we found is that at time 2, up to time 2, we had velocity being positive and negative up to time 6, and then positive after that. All right? So, therefore, here's what we're seeing. If we sort of superimpose, we see that from time 0 to 2, these are opposites of each other. Okay? But if you put in the 4 here, all right, you can see that at time 2 to 6, we had negative velocity, all right? So what we need to look at is one number line with all these times on it. We need to sort of compile these. Oh, you couldn't see that. Let's compile this into one number line, all right? The important times, again, pulling from both number lines, are time 2 seconds, time 4 seconds, and time 6 seconds. All right, let's look at what was going on with each. From 0 to 2, velocity, positive, but acceleration from 0 to 2 is negative. From 2 to 4, we have a negative velocity. But from 2 to 4, our acceleration is also negative. Right? From 4 to 6, our velocity is still negative, but our acceleration is positive. Okay? From 6 on, velocity was positive, and acceleration was positive. And so here's what we're seeing. Velocity and acceleration opposite of each other right here. This is a slowdown. Velocity and acceleration opposite of each other. Slow down. Velocity and acceleration the same. Speed up. And velocity and acceleration the same. Speed up. All right. And whoops, didn't see that. There it is. All right. Whenever velocity and acceleration are the same, you're speeding up. Whenever they're the opposite of each other, you're slowing down. You can just sort of take these two number lines, the previous two number lines, and compile them into one and see what's happening. All right. So with that in mind, another example. With that in mind, let's take a look at another example. Let's say that a ball is thrown upward with a velocity of 80 feet per second, and its height is given by position at time t is given by 80 t minus 16t squared. Now that's the way they write it in the book. I'm not crazy about writing it that way. I'd rather call this s of t and write it as negative 16t squared plus an 80t. All right. So what they want to know is, for example, what's the maximum height reached by the ball? Well, there's more than one way to do this. Hopefully you recognize that this is a parabola and that the maximum value of a parabola is at its vertex. And the vertex is opposite of b over 2 times a. So I'm going to do this using just a little bit of plain old algebra here. Negative 80 over negative 32 is a 2.5. All right. So I just want to show you that your algebra will do this too for you. All right. But we should be doing it with calculus. So how would we find a maximum? Well, the maximum height is going to occur when it comes to a rest. In other words, you throw it up, it momentarily stops, and then it comes back down. It comes to a rest when velocity equals 0. So s prime of t is v of t, which is going to be a negative 32t plus an 80. And velocity equals 0 at 2.5. All right. So again, that maximum could have been found without calculus, but we definitely can do it with calculus. All right. It wants to know what's the velocity of the ball when it is 96 feet above the ground on its way up and on its way down. Well, if we're going to answer that question, the first thing we have to know is when was it at 96 feet on its way up? And when was it at 96 feet on its way down? Since we're talking about 96 feet of height, we're talking about position. So I would take the 80t on a 16t squared and set it equal to the 96. And I'll rearrange this to make it look a little bit better. 16t squared plus an 80t minus 96 equals 0. Just moving some things around. Let's neaten that up a little bit. What I have is a quadratic to solve. I'm going to cheat just a little bit. I have a quadratic solver built into my calculator. I'm going to put in the negative 16, the 80, and a negative 96. And I get a 3 and a 2. So t equals 2, and it equals 3. So basically what happened here is this thing was thrown upwards. And at time 2 seconds, it was at 96 feet. Then it went on up a little bit further. It stopped. It came back down. And at time 3 seconds, it was also at 96 feet. So again, notice to figure out when, this is the when question, to find out when it was at 96 feet, I used the position function. It wants to know how fast it's going. It wants to know its velocity. So therefore, I will have to use the velocity function, which was the negative 32t plus 80. Plugging in those numbers, v of 2 equals negative 32 times 2 plus 80. And negative 32 times 2 plus 80 gives us a 16. And v of 3 is a negative 32 times 3 plus 80, which is negative 16. Does that negative number surprise you? It shouldn't. This just means that it was on its way up at 16 feet per second. And this means it was on its way back down at 16 feet per second. Get used to velocities being negative. It's just an indication of direction.